Testing 1 2. Testing.
So iwe uzansungira bye. So don't bump on the leg. Now you go something All right, guys, so good afternoon. How's been the week? Did we make it to the graduation?
Yes.
How was it? Huh? Okay, so let's keep quiet. I mean, we just are meeting for an hour. So the dimmer the lights, the faster we get home. So the more we talk, we waste time. So I can hear some people saying that they could hear silence by graduation. Huh? So for those of us that were not here, I mentioned that find time to go to such events. You know, it's a motivation. It's not always that you wake up feeling like doing something. So anything that keeps you motivated is really important. Are we together? Yes, sir. All right, great. So last week we did we looked at a YouTube manometer. Okay, so for the sake of, can we keep quiet, please? Na pafupi we. Nemwariri. All right, we just have 30, 40 minutes, not so long, all right? So let's just keep quiet to get the information. And I don't know how you study, but I think this was me even when I was a student. Engineering is not meant to be studied hours on end. If you're doing like 2.5 hours studying, probably your brain is not as efficient at that particular time. Concepts like the ones that we're talking about, go there super fresh, 30 minutes, 1 hour. You get the concept, relax. Then come back again. Unless you're doing these social courses that require you to read and read and read. But I'm sure you've experienced this where you start reading a page, then you know your brain is not, or it needs some more rest. Because if you are that fresh for that particular whatever you're trying to do, 1 hour is super enough. If you want to stretch it, 1 hour, 30 minutes. But hey, that was my style, okay? So do yours. So, I want us to do a revision of what we did last week, because manometers are really important, and anything that will up is just a build-up from what we did. Are we together? And then once we do the YouTube manometer, we'll do another type of a manometer. So last week we talked of one of the simplest ways you can measure, pressure along the water main. Okay, so we said, if this is your pipe, all right, transporting water, and this is the cross section, by the way, so from that other view, it could just look something like this, all right? This is a pipe transporting water, and then you just cut it there, and then you're viewing it from this side. So for some of us that did drawing, if you're cutting a pipe, it will look something like this, yeah? So if you're going to open up and just draw or have a small piece of a pipe, which we can call a piezometer in this case, depending on the amount of pressure you have here, water will flow to that level. Are we together? And this height is very much important. Why? Because from here we can say pressure is equal to what? Mass density of the fluid that you're transporting. So today it could be water, tomorrow it could be oil or mercury or anything. But you need to know what the mass density is. Gravity is always standard, we know what it is. And then the height, this is your height. So the height to which water travels to is very much important. So if you're trying to find pressure at this particular point, this is how you find it. What type of manometer did we say this one was? A piezometer, right? And then we moved on to say another type of a piezometer is a YouTube manometer. Why? Because this guy, I mean, depending on the amounts of pressure that you're dealing with, the more pressure you have, the more height you require. And that is not smart, so to speak, because you end up just traveling 100 meters going up in the air, and then that doesn't serve you well. So we came up with another option, which we are calling a YouTube manometer. So a YouTube manometer Mercedes, huh? Hello? Okay, all right, cheers. All right. Okay, I'll call you when I'm there. All right. Hey, naone kerai. You know, you're trying to cut the cord, but then you can't. This is it. All right, so another type of a manometer we talked about is the YouTube manometer. Why? This one allows us within a shorter space to still read something. And what we said was, if this is your point of interest, let's call it a P, and you allow whatever volume or whatever value or liquid is flowing there, but then on the other end you put what we called a manometric fluid, right? This manometric fluid, one, needs to be higher in mass density compared to. So by having something higher is that no matter the pressure here, it can only push down so far. That's why this works. Because if you put something lighter than what you're trying, then it's just going to get flushed out. Again, you go back to the problems of a piezometer. It's just going to go up. The science behind this is what we were doing last week. So what I want us to do, so before we move on to the next type of a manometer, which is, what is it called again? An incline. It's an incline, right? But we're going to talk about that. So what I want from you, who has the details of what we did last week? So we just do like a quick run of everything. So what were we transporting? What were we transporting? It was water? What was the mass density for this? Are people studying? It was water? What was the mass density of oil? 0.8, right? What else was given? Was this given? What was the height? 1.2 meters. And what was this given as? Okay. And the manometric fluid? What is that? Specific gravity or mass density? 13.1? Okay. What else have I missed out? Chapwai? Okay. Not mass density, right? Okay, cheers. So specific gravity of oil, specific gravity of that value. This is how simple a question would come. And then someone just say, find the pressure, let's say at P. What value did we use last time? It was A. So the question was, find pressure at A. So the properties that we talked about 2 classes before, the relationship between mass density, specific gravity, and specific weight is very much important now. And even if you haven't yet gotten it, there's still time because we are beginning to apply that now. Are we together? So what I said was the best way to go about this is that demarcate the U-tube in the right-hand side section and the left-hand side section. This is very important because we know that fluid that is at the same horizontal line, the pressure is the same, right? So in short, if I'm able to have an imaginary line there and then call this value, let's say K, and then call this value Z, I know my pressure here and my pressure at Z are the same. So whatever equation I can create on one side can be equated to the equation on the left side. And because we're good mathematicians, if we're able to equate these, this will be the only unknown. And then we can proceed like that. Are we together? This principle, it's fairly I can't really say it's the only, but it's the easiest. Okay, you can find different ways to solve the value for P, but this is one of the easiest. All right. So you begin. So let's start with our left hand side. So the pressure at A, so this is what we're looking for, at what pressure is moving in a pipe. So pressure at A plus this guy as oil has got a specific weight which you can derive the the pressure, not so. And we said this should be specific gravity of oil by 1,000. What does this give you? If you multiply specific gravity of oil by, why am I multiplying this by 1,000? So I'm creating a mass density, not so. If you miss the first class, please revise those notes. Just the relationship of those 3 properties. Because if you miss it there, then all these numbers will just be flying. So if we have a mass density, then I'm going to have my gravity, and my height is what? 1.2. And I can call this is equal to pressure at what? Let me do that. So pressure is just pressure. Okay, whatever this weight is sitting on my hand, and if I put on top a phone, the pressure increases, right? It's basically the same of whatever is happening here. So your interest is what pressure is sitting here. The pressure sitting here is the pressure flowing at that particular point that you're looking for, which is what we've written, plus the pressure due to the column of this oil. So when you add these 2, the pressure comes to sit there. Are we together? Then you go back again. You come and say, what is my right hand side? Again, all you want to do is find the pressure at Z. Because the end game is if I equate the pressure at Z and the pressure at K, then my equation will just cancel each out and I'll find out whichever one is sort of missing. Are we together? So how do I find my pressure at Z? So anything that is open to the atmosphere has got a pressure called 0. It's when you expose it to the atmospheric pressure, your pressure will be 0 on top there. Are we together? All right. So I can say okay, let me call this point D. All right. So the point D is the one just seated just on top of the surface there. So pressure, okay, at D plus what you are given is the mass density for this liquid. So from the specific gravity rather, you can derive the mass density. So you just need to multiply your 13.1 by 1,000 When you close this is your mass density. In short, this is that value. And whatever is going on here, this is that value. If you multiply this by 9.81 and multiply this by our height, and this will be your pressure at what? At Z. You and I, 2 classes prior, we discussed that, or we discussed the law of Pascal, right? Pressure at a point is the same from all right? And fluid, or pressure rather, only varies with depth, okay? So pressure here and pressure here and pressure there are all what? They're different, right? And you expect X to have the most pressure, not so. But if I maintain the value or the position of X, and then I say what is the pressure here and here, P and maybe M. P, X, and M are the same. Even here, that principle is still maintained, and this is what we're applying. Because the pressure at K and Z are the same, so this equation can be equated to this. But then this is equal to 0 because it is exposed to the atmosphere. Most of the times it's exposed. And I think I didn't really mention this the last time we met, right? But in the YouTube manometer, which is open, which is usually the way it's supposed to be, this will be exposed, so your pressure there will always be taken as a 0. In the coming classes, we'll explain why exactly the value here is a 0. And once you equate this equation to that equation, you find that this will be the only guy out time. So in your own time, confirm this value individually, and then find time to also compare to the next person. So this is a recap of what we did last week. So let's try to learn from what. Can I erase this? All right. All right, so today let's talk about a differential manometer. Okay, so just a differential, is there an example here? So, please don't bump the camera. So, a differential manometer. What do you understand by that phrase? Yes, I can hear something here. I know, sir. Ena miona mumuseka munzano imi na kusogoro kwa kambaka. You're about to start having elections? When is it? Oh, in November? Bamba fast, eh? Anyone standing here? You will be? Okay, what position? President. But can you be a president as a fresher? You will? What position? Committee member. Okay. You guys can only become vice presidents, right? No, wait a minute. A first year can be a VP. Yes. Yes, that's the highest you can get. Huh? Okay. All right, so let's write something about a differential manometer. Let's keep quiet, please. We're almost leaving because it's getting dark in the next 15 minutes. So let's write this. To measure the pressure difference between 2 points, to measure the pressure difference between the 2 points. To measure the pressure difference between 2 points, we use a U-tube manometer as shown. A U-tube manometer as shown. Shoot. So I said to measure the pressure difference between 2 points, we use a U-tube manometer, obviously, as shown. So this is not what I was looking for, but we can work. Can we? Okay. All right. So a differential manometer is a manometer that allows us to measure the pressure difference. So it can be 2 pipes, 2 separate pipes, or just 1 pipe. Okay? So one, it can be this one very pipe, and then it gets connected in that sense. Okay? So meaning what you're interested in that one pipe, one water main, this could be a point, maybe you're calling this Z, and you're calling this point as well, maybe X. What you want is the pressure difference, because in fluid mechanics, the fact that these 2 points, first of all, are differing in altitude, yeah, or in elevation. Thank you for that. It already means that the pressure will be different between the two. Also, because what is here and there's a distance in between that will also cause a difference. And then there could be other issues that are in between that pipe. Are we together? Alternatively, you can also have a pipe. So this is from a cross-section point, and you also have another pipe. And maybe these pipes could be different. Maybe this one is got a smaller size, okay, by diameter, than the other one maybe is bigger. And they are running maybe in the same way or vein. So you can connect something that allows you to measure pressure. All right? In that sense. So you want to find the pressure difference. So you're not finding the pressure here and here per se, but the equation you're going to create between or by virtue of having this relationship will give you the difference. So this could be a 10, this could be a 4. The value you're going to get is a what? If this is a 10 Pascal and a 4 Pascal, what would be your value here? It's just a difference that you're going to get. So you won't solve exactly for this point, no, and that point, but the equation you're going to create, it will be in a way that the pressure here minus this pressure here, it comes out as 6. So it's just a pressure differential manometer. All right, so let's try to illustrate this further. And I think you have this in your modules. Let's just try to fully understand what is going on. Should I maintain the values? Okay, let me just maintain. All right, put your value here as a B and an A, and then there is that line which makes things basically the same. And then whatever you're carrying this side flows through one side. You are assured of it flowing through all the way up there, and then it comes down to this point. So from this drawing or illustration, the water, if we're dealing with water in this case, that is flowing on one end is also coming to the other end. It's also pushing down. So you find that the levels here gets to drop up or down, okay? And What you also notice is that you've got a manometric fluid. So they're calling this value a D, and this one is a C. So they're just calling this a manometric liquid. I don't know why they're calling it Q of mass density. Usually they'll just mass density manometric. Huh? And then points of interest, how far is point A? How far is point A, okay, to the line that is very common? So they'll just use, let's say, value A. Then how far is B to the point of interest? Okay, so capital A and the A, capital B and the B. And then whatever is here, they're just calling it fluid P dash of density, just that. Okay, so CC, I don't think we've missed anything. Don't worry about the design, it could be different, but what's important is that the U-tube manometer will always have a manometric fluid, and depending on the pressure here and the pressure there, when water is flowing, this point of C could either go down or up. The value here as well could either go up and down. So there's also a value called H here, which is very important, just to the levels to which the manometric fluid has gone to. Okay, so then you say, using the same approach, as before, of course, pressure at C, which is pressure C, is equal to pressure at D, which is denoted as a P and a D there. Okay? So this is always a starting point. This is always a starting point. So if you go through whatever we did on the left side, on the right side, it will take you to this point. So you'll come and say, so therefore, pressure at A plus rho gravity A is equal to pressure at B plus rho gravity open bracket B minus H plus mass density of the manometric fluid, gravity, and the height. So meaning on the left-hand side, this is the equation that you're going to create. Pressure at A is equal to mass density of this liquid, which is where we are here, by gravity, by the depth, not so, which is A. And this is how this equation was born or has been created. Are we together? So this is on the left-hand side. Then on the right-hand side, how do you find the pressure at D? All right, it's pressure at B, okay, plus mass density, which is this one. The mass density here is basically the same. That's why the rho is just the same. Okay, plus gravity, open bracket, B minus H. So B minus H, so you just remain with that value because this is what we're ending for now. Are we together? The goal is to come and reach where D is. So how do you get to D? So it's going to be pressure at B plus mass density of this guy by gravity by this height plus mass density of this guy by gravity by this height. Are we together? So you cannot get B and use it under one fluid. Why? Because these are two different fluids and they have got two different mass densities. Are we together? Come on. Done? Mercedes, huh? Okay, I'm starting off now. Okay, so did we get how this is coming about, yeah? On D. Let me repeat this one more time. Mass density, the pressure at B, so this is where this guy is standing, plus what is the mass or the pressure due to this guy? It's going to be mass density of this same liquid by gravity by this height. But then how do we get this height? If you subtract H from B, you're going to get the difference. And I'm going to show you why we're trying to just work with the value of H. So this is what's happening here. You want to find that difference. But then it doesn't end here because we've just reached here. Remember, we're trying to equate C and D. So the other piece is going to be the mass density of this guy, mass density of manometric by gravity by the H. So the H is the one that is standing here. Okay? And then you are equating the two. So hence, the pressure difference is, so pressure at A minus pressure at B is equal to rho gravity, open bracket B, minus A, open bracket, plus H, G, this is mass density manometric, minus. But I'm not worried about whatever has come from where because we're good mathematicians, eh? Did I mention that we... We are good mathematicians, eh? So this is not a problem. So, you know how to factor what and how to make, what subject was that again? Like terms, how to substitute this so that you're working with one terminology, right? This is what's just happening here. So as long as you've got your B, you've got your A, and you've got your H, the value you'd be found. Okay? What would be interesting, this guy doesn't have an assignment or an example. Okay, so we're going to give each other an assignment today. When are we meeting? Thursday. And I need this assignment on Thursday. No. Kule mbafe bagamba. Just like this. Just write. The typing bit is when you are, maybe you're writing something very long, but here we calculate. Typed. You ain't going to solve and everybody has solved. Just be copy and paste. Have the same stuff everywhere. Okay? So, let's maintain this. I'm just going to give values in terms of what can be a specific gravity, a specific weight, and all that. Can I erase this part or I leave it? Okay? So example, maybe just this is one. So this is an assignment. Oh yeah. Ufuna quiz eh? Don't worry, it's coming. Yes, there's a question. Oh, yes, sir. Someone has got a question. Let's just listen to him and then, yes, sir.
Is it effective to, or is it okay to say pressure B minus pressure A? Or it's just the same?
Oh, you mean like this one?
Yeah, what if maybe you switch them? Is it still going to be the same thing?
Oh, yeah, very good question, very good question. So, what sometimes happens is you don't know, if you were to tell me between B and A, which one has got a bigger pressure? Okay, but you see that doubt of I'm not too sure means that, it's a very good question, thank you for that, means that sometimes you can swap these and your answer would come out as a negative. That should not scare you because you're just looking for the difference. Are we together? So if you had swapped, or if you had put maybe this equation on the other end and you have B minus A, your answer maybe would be a negative. Are we together? So the fact that you're dealing with difference, it's just a difference. It doesn't matter which one is low, which one is up. What you just want is the difference. Does that make sense? So this is one good sort of subunit or topic where you can have an answer which is negative. But then at the end of the day, if you find your answers, let's say negative 10 pascals as your difference in pressure, just come and say, therefore, the difference in pressure is just 10 what? Pascals. So the negative just means that you assumed one point to be higher in pressure compared to the other. It should not scare you. Where values will be negative, I'll tell you that on this subunit, if you find a value which is negative, either you've done this or it means something like this. Yeah? Okay, so make use of this drawing the way it is, untinted. So I'm just going to give you what those are. So take A as 1.5 meters. Let's get our B as a 2.2 meters. Hold it. Let me make it interesting, huh? Let me make it interesting. Yeah, let me make it interesting. Ooh, this is great. This was so boring. So, between this point and this point, take the difference as 5 meters and take the angle as 30 degrees. Yep, that looks good. That looks good. You guys are mathematicians, right? So, the difference between A and B is 5 meters. The angle differentiating their altitudes is 30 degrees. Exactly. Someone's even mentioned how you go about it. And then, is that a boy? So, angle difference take as 30 degrees, and let's say horizontal distance is equal to 5 meters. Then take your h. So your h is still the same one. Take your h as, okay, maybe let's just put it at 1 meter, just to be safe. Are we together? And your manometric fluid has got a mass density of 12,600. And the fluid that you're transporting, all right? So the fluid P, yeah? So fluid P Fluid P, so let me put it this way. Mass density of fluid P is equal to 800. Okay, so 1, 2, 3, 4. Yep, this looks interesting. Okay, so this is your question. Okay, so you are submitting this the first thing when we meet on Thursday. What's happening on Thursday? Is this clear, guys? And before someone gives me a call to say something is missing, nothing is missing here. If you're not finding it, just means that you're stuck somewhere. Just try to consult. Yes, sir?
This main pipe which comes from Kafue to Lusaka.
Yeah. Someone's got a question. We're almost done.
The pressure which starts from Kafue, is it the same if it's in a straight line? Will the pressure be the same from Kafue to Lusaka?
So, ideally, if there are no leakages along the pipe, and I'm talking about a pipe which is like super horizontal, the pressure here will be the same as that pressure. But those are not realistic goals you'll find. Because between Kafue and Lusaka, trust me, there are leakages. And those leakages will have in them air in it. Part of the water is leaving. Part of those walls probably have become smaller. And the more you constrict or reduce in the diameter size, the more pressure differences will begin to happen. So usually you will find that there's a difference between those 2 points. No matter the same diameters and the same elevations. Yeah, but in a perfect situation, it should be the same. So the pressure differences should be 0. Yeah. Okay, are we good, guys? So we will see you on a Thursday. Bring my assignment. What I can encourage you is the first thing on meet. What I can tell you, what we've done with the piezometer, with the YouTube manometer, which is simple, there are many other examples of past papers out there. Practice as much as you can. Even by the time you'll be getting here, it's just going to be that easy. Even for the pressure differences, they are also different. What we have covered so far is enough to say 50% of an exam came. Just what we've done so far. Yes, so if you get this point well, everything gets easier. All right, so see you on Thursday.